Hi, we today are going to continue working on, and we're really moving in now to the, let me get my pen working, the inferential statistics. So we're going to truly begin that today, and we are going to talk about the theory. And the theory is we need a very special theorem called the central limit theorem. In order for us to move forward in the inferential statistics side. And it says a couple things, okay? One thing it says is that regardless of the underlying distribution of a population, the sampling distribution of the mean is always normally distributed. Okay, so that's one thing that it says. And it also says, and the mean of the sampling distribution is the same as the mean of the population, and standard deviation is the standard deviation of the population divided by the square root of n. So that says kind of a lot in English right there. What it says sort of in mathematical notation is that x bar is normally distributed, and the mean of x bar is the same as the mean of the population, and the standard deviation of x bar is equal to the standard deviation of the population divided by the square root of n. So we're going to use this fact a lot. And the reason why we're going to use that fact is because we will infer, which means make conclusions, about a population mean based on a sample mean. And we will do that in confidence intervals and hypothesis testing. So this is the last kind of big statistical idea we need to do before moving on to the two variable. In some classes you've already done the two variable, but these are the two topics that we really need the theory of the central limit theorem to move forward. So what I want to do is kind of show you an example with a sampling distribution so that you can kind of see the central limit theorem take place, okay? so instead of proving the theorem, which takes a little more math than you guys have under your belt, I'm going to show you using an example because I feel like maybe you'll be able to see that better. Okay, so here's my example. Given the population of 3, 4, 5, 6, and 7, okay, we have the x, p of x, so this is a discrete distribution, right? This is discrete, and x is 3, 4, 5, 6, 7, and the probability of getting a 3 is 1 out of 5, 4 is 1 out of 5, 5 is 1 out of 5, 6 is 1 out of 5, and 7 is 1 out of 5. So this is a uniform, discrete distribution, and if you were to graph it, you would graph it to be 1/5 is the probability, or 20%. There's 1, there's 2, there's 3, there's 4, and there's 5. Okay, so that is the population distribution. Okay, now what the central limit theorem says is let's take the sampling distribution for this. Okay, so I have never really shown you this before, but it's like building the probability sample space. So with that distribution, I'm going to build the sample space if I'm going to sample of size 2 without replacement. Okay, so I'm going to give you the following is the sample space. Okay, or what we call the sampling distribution. So that's kind of a new word. We've talked about sample space, but not so much sampling distribution. So remember that the population is 3, 4, 5, 6, 7. So just imagine that you have little balls in a bag. Each one has one of those numbers on it. So there's 5 balls in a bag. One is labeled 3, one is labeled 4, one is labeled 5, one is labeled 6, and one is labeled 7. And you reach your hand in that bag and you pull out a 3. And then you put it back in and you get another 3. Okay? Or you could have pulled out a 3, reached back, put it back in, reached in and got a 4. Or you could have pulled out a 3, put it back in, reached in, got a 5. You could have put in a 3, and so forth. So this is without replacement, putting in, picking a 3 out of a bag, putting it back in, and pulling another 3 out of a bag. You could do the same thing for the 4s, right? That you pull a 4, put it back in. You could have also pulled a 4, put it back in, and pulled out a 3. I'm going to erase just the order I've done that because I think it will look better in notes. So you pull a 4, put it back in, pull a 3, then you pull a 4 and a 4. You could then pull a 4 and the 5. You could pull a 4 and a 6, or the 4 and the 7. Okay? Same thing with the 5s. You could have done 5 and 3, 5 and 4, 5 and 5, 5 and 6, and 5 and 7. And then with the 6s, 6 and 3, 6 and 4, 6 and 5, 6 and 6 and 6 and 7. And then again with the 7s. 7, 3, 7, 4, 7, 5, 7, 6, and 7, 7. Okay, so what's going to happen now is that I'm really interested in seeing the distribution of the means of this. So this is the sample space, the sampling distribution, and what I'm going to find for each one of those is the x bar. So between 3 and 3, x bar, the average, is 3. The average of 3 and 4 is 3.5. The average of 3 and 5 is 4. The average of 3 and 6 is 4.5. And the average of 3 and 7 is 5. Okay, now I'm going to do it again for the next line. The average of 4 and 3 is 3.5. The average of 4 and 4 is 4, and so forth. The average of 5 and 3 down here is 4. The average of 5 and 4 is 4.5. The average of 5 in itself is 5. The average of 5 and 6 is 5.5. And the average of 5 and 7 is 6. Keep going. The average of 6 and 3 is 4.5. The average of 6 and 4 is 5. The average of 6 and 5 is 5.5. The average of 6 and 6 is 6. The average of 6 and 7 is 6.5. The average of 7 and 3 is 5. If you don't know how I'm getting these numbers, I'm just adding 7. I'm just adding 7 plus 7 and dividing by 2, or adding 7 plus 6 and dividing by 2. So I'm just finding the average between those two numbers. Okay, so now what I want to do, which may seem like kind of novelty idea, is that I want to find the mean of all those x bars, which just means the average of all these red numbers that are here. So I'm going to go ahead and do that by using the formula, right? So I'm going to add 3.5 up, 4 up, 4.5 up, 5, 5.5 up, and all of that. But before I do that, maybe we should graph it so we can see what it looks like. Okay? So if I take this, I'll do red, and I do the sampling distribution. Okay, the sampling distribution consists of the numbers between 3 and 7, right? So those are the numbers, right? The sampling distribution is 3, 3.5, 4, 4.5, 5, sorry, 5.5, 6, 6.5, and 7, right? Those are the only numbers that show up in my sampling distribution. Notice these numbers here are very different, though some repeat, of the numbers in the population. And the sampling distribution also has a a formula that goes with it, which this is my x bar value, and this is the probability of x bar happening. The x bars are kind of all those numbers there, which are 3, 3.5, 4, 4.5, 5, 5.5, and then we have 6, and then we have 6.5, and then we have 7, right? And each one has a probability associated with it based on the overall sampling distribution, right? How many are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, right? So there's 25 total in this distribution. That's probably good to know. N equals 25. Whereas previously in this distribution, right, N is 5, right? So there's 5 of those there. And we also could do the mean and all of that then. But here in this distribution, if we go down here, we can get the probability, right? So look at all these red numbers. How many times do you see a 3 come around? Well, 1 time, right? So the probability of that X bar is 1 out of 25. Now, how many times do you see a 3.5 come around? Well, 2 times. How many times do you see a 4 happen, right? So a 4 happens 3 times. And you can see that a pattern's going. That's why I wrote the numbers the way I did. 4.5 happens 4 times. And 5.5, 5 happens 5 times, that diagonal. And 5.5, we start to go down again, happens 4 times, and so forth. And we could go ahead and also graph this, right? Where this axis is the X bars, and this axis is the probability that those X bars happen. And here we can go all the way from 1/25 to 5/25. So we have 2/25, 3/25, 4/25, right? And we could graph this. So this is 3, 3.5, 4, 4.5, 5, 5.5. Oops, I hope I don't run out of room. 6, 6.5, and 7. Okay. So if we graph it, the 3 happens 1. 3.5 happens 2. 4.5 happens 3 times. Oh, sorry. The 4 happens 3 times, yes. And you can see that this distribution does in fact kind of take on a normal shape, which is what excuse me, the theorem says. It says that the means of the sampling distribution is the sampling distribution of the mean is always normally distributed. So you can see that even in this simple discrete example, when we started with a uniform distribution, that does not look normal at all, right? It's big flat across the top. That once we took its sampling distribution of size 2, we got all of these means out, and when we graph those means, it looks normally distributed. So that's one thing that the central limit theorem says. Okay, it also says some other things. So that's what I want to do now, okay? So in my new Actually, let's just go back and see if I can do it by extending the page. Yes, okay. So now what I want to do is I want to find the mean of x bar. And you can either do it by adding them all up and dividing by how many you have, or you can do it by using the distribution, that 3 times 125, 3.5 times 225, all of that. I'm going to do it. It doesn't really matter which way you do it, but the mean in this case is add up all those numbers, right? So there's 3 plus 2 3.5s, right? There's 2 of those. So I'm really just going to, I'm doing the sum right now, so I don't need that notation there. Plus 3 times 4 plus 4 times 4.5. And if you're wondering where I'm getting these numbers, they are coming directly from, there's 4 of those 4.5s. Now there's 5 of those 5s. Go back and look at the chart and you'll see that that's how many of each number there are. Then there's 5 of 5, and there's 4 of the 5.5s. There's 3 of the 6s, right, from the chart. There's 2 6.5s, and there is 1 and there is 1 7. Just like there was 1 3 at the beginning. We can even write that there if we need to. Okay, so if you add all that up and so you're going to take all those, you're going to add all those up, and then you're going to divide by 25 because that's how many there are. And when you do that, the answer will be 5. Okay, so you can verify that by adding all those up and doing that. The other thing to notice is that up here, kind of in this population, right, if you find the average of that, the average is 3 plus 4 plus 5 plus 6 plus 7. In this case, you're going to divide by 5, and that number is also 5. So that is one part of what the theorem says. It says that the averages between the plane distribution and the sampling distribution of the means are the same, and we found that. We found that they were both 5. Okay, the other part of what the theorem says is that if we want to find the standard deviation of x bar, right, what we do is we add up, right? The formula is we take all those x bars, we're going to subtract the mean of those x bars, we square it, and we divide by how many we have, right? This is a population standard deviation, so we divide by how many we have, not n minus 1 of how many we have. That's the sampling standard deviation. So here, if we do this formula, I'm going to show you part of it, right? So you have 1 x bar is 3, and you're going to take away the mean 5, and you square it. And then you have 2 of those 3.5s, and you take away the mean 5, square it, and so forth, until you get to the other end when you have 2 of the 6.5 minus 5, and you square it, and then you add to it the 1, 7 minus 5 squared. Okay, so that's adding it all up, and then you divide all those sums after you find them by 25. And what you'll find is, in this case, that that number happens to be 1, which seems kind of crazy that all that works out to be 1, but it does. Okay, so I want you to keep that 1 down here in mind. And then I want you to go up here kind of with these numbers and find, I'm going to do it over here on the side, the standard deviation of these 5 numbers, which again is 3, take away 5, square it, 4, take away 5, square it, 5, take away 5, square it, 6, take away 5, square it. All of that, and you'll find that the standard deviation of that is the square root of 2. And you say, whoa, wait a minute, because this is the square root of 2, and this is 1. So how does that work? Okay, so I want you to go back and realize, right, this is what the theorem says. We already found, right, in our example that 5 equals 5. Okay? In the standard deviations, we found the standard deviation of x bar to be 1, and we found the standard deviation of sigma to be the square root of 2, right? That this number right here is the square root of 2. Now, what was this n in this situation? It's not 25 nor 5. It is the fact that we took a sample size of 2. Okay, that's the way the experiment worked, is we took a sample size of 2, that 3, 3, 3, 4. And so if we go back here, our square root of n is in fact the square root of 2, which is 1. So you can see 1 equals 1, and this part of the theorem is true by example. I would prove it mathematically, but the math to do that with all the formulas is just a little bit, I think, too much at your level. So I do it with an example to prove to you that this really works. Okay, so in hindsight, no matter what the distribution of the overall population is, if you take every single sample of any size, in this case we just did size 2, the mean of the sampling distribution is the same as the mean of the population, and the standard deviation is the standard deviation of the population divided by the square root of n. Okay, so we're going to use this for kind of some examples. Okay, so here is an example I want to write up kind of in practice that uses the idea of the z-scores and all of that that we've worked on before. Okay, so if a population has a mean mu equal 80 and sigma, the standard deviation, equal to 8, determine the parameters of the sampling distribution. Which means the mean and the standard deviation of a sample from this population of size 16. Okay, so what that means is, if we break it all down, is that mu equals 80, sigma equals 8, and n equals 16. N, of course, is the sample size. So therefore, the parameters of the sampling distribution are mu of x bar, sigma of x bar. Mu of x bar is the same as the mu of the population, so it's just 80. Sigma of x bar is always equal to sigma from the population divided by the square root of n. In this case, it's 8 divided by the square root of 16, which is 8 divided by 4, or 2. So this is the mean, and this is the standard deviation of the sampling mean. And I could go a little further and kind of ask another question, which is, out of this distribution, sample, what is the probability that the mean is between 76 and 84. Okay, so it's the same kind of probability questions that you did when you dealt with the normal distribution. It's still the same thing because it's normally distribution. The key here is that it says, what is the probability that the mean? It's not the probability of the scores, it's the probability of the mean. So in this case, we'd say we're asking what is the probability that the mean is between 76 and 84. Okay, and because the mean is normally distributed, we use z-scores. Okay, so we would go there and we would convert it to a z-score. So we're going to say, well, this is the probability that 76, and we'll take away 80 because that was the mean, but in this case we're going to divide by that 8 square root 16 because we're talking about the mean. That transfers the mean to z, and then we do the same thing on this side. And we end up with, what is the probability that I'm between, this is -4 divided by 2 is in between z, which is 4/2, which is the same as saying the probability that I'm between -2 and 2. And we know that by using the empirical rule, that what that means is if this is 0 and this is 2 and this is -2, I want this probability in here, and we know that that probability in there is 95%. So the answer is 95%. And you can use the normal distribution the same way you've been using the normal distribution, but in this case what's so incredibly different is that you're dividing by a different standard deviation, and what's controlling that standard deviation is really the central limit theorem. So that's my lecture on sampling distributions, and we're going to move forward and then use the sampling distributions to talk about confidence intervals and hypothesis testing. So the next set of lectures will be all about confidence intervals. Okay.